Differential equations, growth and decay. This lesson teaches how to use separation of variables to solve a simple differential equation. We will use exponential functions to model growth and decay in applied problems. Solve the differential equation of y prime is equals to 3x over y. To solve this, y over dx is equals to 3x over y. We will cross multiply is equals to 3x dx. Then we will integrate 1/2 y squared plus c1 is equals to 3x squared over 2 plus c sub 2. Not necessary to add constants to both sides. Y squared is equals to 3x squared. We will obtain a general form of y squared minus 3x squared is equals to 0. Decay models. Consider the statement, the rate of change of some quantity y is directly proportional to 1. This dt is the rate of change of y is directly proportional to y. If y is a differentiable function of t such that y is greater than 0 and y prime is equals to k times y for some constant k, then y is equals to c raised to k times t, where c is the initial value of y and k is the proportionality constant. When k is greater than 0, exponential growth occurs. And when k is less than 0, exponential decay occurs. The differential equation dy over dt is equals to ky. We will separate variables. 1 over y dy is equals to k dt. Then we will integrate. It will result to ln of y is equals to kt plus c. Then exponentiation. E ln of y is equals to e raised to kt plus c. We can now cancel exponential of ln. Y is equals to e raised to kt times e raised to c. Y is equals to c e kt. This is our final answer. Radioactive radium has a half-life of approximately 1,599 years. What percent of a given amount remains after 100 years? In this problem, we will use the formula y is equals to c times e raised to k times t. C is not given, so we have a 1/2 c in 1,600 years because of the half-life. T is given, which is the 1,599 years. will divide it by C. One half is equals to the remaining part, E raised to 1,599k. And by exponentiation, we will have ln of 1/2 is equals to ln E 1,599k. ln of 1/2 is equals to 1,599k times ln of E. We can now cancel. Then, to get the k, we will divide it by 1,599. Then, cancel. K is equals to negative 0.0004. Is equals to 100. We can now substitute it with the formula CE raised to KT. CE, where the K is equals to negative 0.0004 times the time, which is 100. Y is equals to 0.9576C. The final answer will be 95.76% remains after 100 years. The rate of change of y is proportional to y. When t is equals to 0, y is equals to 3, and when t is equals to 2, y is equals to 6. What is the value of y when t is equals to 3? In this example, we will use the initial condition, t is equals to 0 and y is equals to 3. Y is equals to 0. We will substitute the 3 and the 0. We can now cancel out and we can get C is equals to 3. Also, in this given initial conditions, by this given formula, 6 is equals to 3e2 times k. To solve the e, we will divide it by 3. Then we will ln both sides. We will bring down the 2k. Then to get the k, we will divide it by 2. So k is equals to 0.3466. To find y when t is equals to 3, we will also use the formula C e raised to k times t. Then direct substitution. C is equals to 3 e, then the k 0.3466 times the given t. The final answer is 8.485.
Suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original population? So let y is equals to c e raised to k t to be the number of flies at time. T where is measured in days, because y is equals 100 when t is equals to 2 and y equals 300 when t is equals to 4. You can write 100 is equals to CE raised to 2k and 300 is equals to CE raised to 4k. From the first equation, you know that C is equals to 100, E raised to negative 2k. Substituting this value in the second equation produces the following. 300 is equals to 100 e raised to negative 2k e raised to 4k. 300 is equals to 100 e raised to 2k, where ln of 3 is equals to 2k. Multiply both sides by 1/2, so the 2 will be cancelled and the k will remain. Makes it 1/2 ln of 3 is equals to k, and k is equivalent to 0.5493. So the exponential growth model is shown as formula y is equals to CE raised to kt, substituting the k as equivalent to 0.5493. Y is equals to CE raised to 0.5493 times t. To solve for c, reapply the condition where y is equals to 100, t is equals to 2, and obtain 100 equals to CE raised to 0.5493 times 2, where c is equals to 100, e raised to negative 1.0986 is equivalent to c equals to 33. Suppose that 10 grams of the plutonium isotope Pu-239 in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? Solution. Let y represent the mass in grams of the plutonium. Because the rate of decay is proportional to y, you know that y equals to c e raised to kt, where t is the time in years. To find the values of the constants c and k, apply the initial conditions using the fact that y equals 10 and t equals 0. You can write that 10 is equals to CE raised to k times 0, so equivalent to CE raised to 0. Which implies that c equals 10. Next, using the fact that y equals 5 when t equals 24,100, you can write the 5 equals 10 e raised to k times 24,100. 1/2 equals to e raised to 24,100 times k, given to 1 over 24,100, and then of 1/2 equals to k. So k is equivalent to negative 0.00002871. So the cooling model is, the half-life model is equals to y equals 10 e raised to negative 0.00002871 times t. To find time, it will take for 10 grams to decay to 1 gram. You can solve for t in equation t. 1 equals 10 e raised to negative 0.00002876 times t. So t is equivalent to 80,000 years. The half-life of a radioactive material is T equals to 5,730 years. If a material sample contains 14% of the original amount, find the date the material sample was created. Solution. Let us fix the time of the original amount at T equals to 0. And denote the present time by T1. Also denote Y of T as the material amount at time T. Y of T is equals to Y initial T raised to negative KT. Y initial, by simplifying and transposing, is E raised to negative KT sub 1 equals Y of T1 was 14 over 100 Y of 0 equivalent of 14 over 100 Y initial. So Y initial, E raised to negative KT sub 1 was 14 over 100 Y initial, and negative KT sub 1 equals ln of 14 over 100. So T1 is equals to 1 over K ln of 100 over 14. Recall as T time as ln of 2 over K, and time is equivalent to 5,730 years. So 1 over K equals to 5,730 over ln of 2. We obtain T of 1 well, 5,730 over ln of 2 times ln of over 100 over 14. Hence that T sub 1 equals to 16,253 years.
Newton's law of cooling or heating. If the rate of change of the temperature T of the object is directly proportional to the difference in temperature between the object and its surroundings, then we get the following equation where K is a proportionality constant. We have the derivative of temperature over the derivative of time is equals to K times M minus T, where K is greater than 0. The T here is the temperature of an object, while the M is the temperature of its surroundings, and T is the time. As the differential equation is separable, we can separate the equation to have one side solely dependent on T, and the other side solely dependent on the time. We have the derivative of temperature over M minus T is equals to K dt. We will integrate both sides. Then the answer will be ln times M minus T is equals to KT plus C. Then we will simplify. ln is equals to M minus T is equals to negative K times T minus C. We will use exponentiation. ln M minus T is equals to negative KT minus C. We can now cancel. Then we will have M minus T is equals to raised to negative KT minus C. This is our formula for Newton's law of cooling or heating.
You can find the temperature inside your refrigerator without putting a thermometer inside. Taking a can of soda from the refrigerator, let it warm for half an hour, then record the temperature. Let it warm for another half an hour and record its temperature again. Suppose that the reading RT of 1/2 is equal to 45 degrees Fahrenheit and T is of 1 is equals to 55 degree Fahrenheit. Assuming that the room temperature is 70 degree Fahrenheit, what is the temperature inside the refrigerator? Taking the 1/2 hour after the soda was removed from the refrigerator to be the zero time, and stating the given information in an appropriate way, we have the boundary value problem. So we have dt over dt is equals to k times 70 minus t is equals to t of 0 is equals to 45. T of 1/2 is equals to 55. And we know that the solution of this boundary value problem is t is equals to 70 minus 25 times 3 over 5 to the power of t times time. To check this formula for reasonableness, we observe that the formula gives us t of 0 is equals to 70 minus 25 times 3 over 5 to the power of 2 times 0 is equals to 45. And t of 1/2 is equals to 70 minus 25 times 3 over 5 to the power of 2 times 1/2 is equals to 55. The temperature of the refrigerator is the temperature of the can of soda. At time T is equals to negative 1/2. So we can see that the temperature of the refrigerator is T of negative 1/2 is equals to 70 minus 25 times 3 over 5 to the power of 2 times negative 1/2, and is equals to 70 minus 25 times 5 over 3. And we can get the answer 28.3 Fahrenheit.
Let y represent the temperature in degree Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. If the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? So, from Newton's law of cooling, you know that the rate of change in y is proportional to the difference between y and 60. This can be written as y prime equals to k times y minus 60 and 80 less than equals y is less than equals to 100. To solve this differential equation, use separation of variables and integration. Differential equation of the equation is dy over dt equals k times y minus 60, separating variables by 1 over y minus 60 times dy is equals to k dt. Integrating each side by integral of 1 over y minus 60 dy is equals to integral of k dt. Finding the antiderivative of each side is equals to ln absolute value of y minus 60 is equals to kt plus c1. Because y is greater than 60 and the absolute of value of y minus 60 is equals to y minus 60. And you can omit the absolute value signs using exponential notations. You have y minus 60 is equals to e kt plus c sub 1, and y is equals to 60 plus ce raised to kt, as c is equals to e raised to c sub 1. Using y is equals to 100 when t is equals to 0, you obtain 100 equals to 60 plus ce raised to k times 0 equals 60 plus c, which implies that c is equals 40 because y equals to 90 when t is equals to 10. 90 equals to 60 plus 40 e raised to k times 10 equals to 30 equals 40 e raised to 10k. K is equals to 1 over 10 ln 3 over 4. So K is equivalent to negative 0.02877. So the cooling model is Y is equals to 60 plus 40 e raised to negative 0.02877 times t. And finally, when y equals 80, you obtain 80 equals 60 plus 40 e raised to negative 0.02877 times t. 20 is equals to 40 e raised to negative 0.02877 times t, as 1 half is equals to e negative 0.02877 times t. ln of 1 half is equals to negative 0.02877 times t. We use ln to cancel the e. So, t is equivalent to 24.09 minutes.
In a murder's investigation, corpse was found by a detective at exactly 8 p.m. being alert. The detective also measured the body temperature and found it to be 70 degrees Fahrenheit. 2 hours later, the detective measured the body temperature again and found it to be 60 degrees Fahrenheit. If the room temperature is 50 degrees Fahrenheit and assuming that the body temperature of the person before the death was 98.6 degrees Fahrenheit, at what time did the murder occur? So, the solution for this is with time 0 taken to be 8 p.m., we have the boundary value problem. Derivative of temperature over derivative of time is equals to K times 50 minus temperature. T of 0 is equal to 70 and T of 2 is equals to 60. Whose solution is T is equals to 50 plus 20 times 1 half of T over 2. We would like to find the value of T for which T of temperature of T is equals to 98.6 degree Fahrenheit. Solving the equation, 50 plus 20 times 1 half to the power of T over 2 is equals to 98.6 degree Fahrenheit. Give us T is equals to 2 times ln of 48.6 over 20 divided by ln of 1 half is equals to negative 2.56. It appears that this person was murdered about 5:30 p.m. or so. Here is a graph of the function. 5:30 p.m. T is equals to 50 plus 20 times 1 half to the power of T over 2 over the interval of negative 2.56 less than T less than 2.56.
Midnight with the temperature inside your house at 70 degree Fahrenheit and temp outside at 20 degree Fahrenheit, your furnace breaks down. 2 hours later, the temperature in your house has fallen to 50 degree Fahrenheit. Assume that the outside temp remains constant at 20 degree Fahrenheit. At what time will the inside temp of your house reach 40 degree Fahrenheit? Solution boundary the problem that models this equation is derivative of temperature over derivative of time is equal to K times 20 minus temperature. And T sub 0 is equal to 70 and the T sub 2 is equal to 50. Where time 0 is midnight, the solution of this boundary problem from the work done in the problem number 1 above is T temperature equal to 20 plus 50 times 3 over 5 raised to t over 2. For the purpose of the reasonable check, that this formula give us t sub 0 is equal to 20 plus 50 3 over 5 and raised to 0 raised to over 2 is equal to 70. And t sub 2 equal 20 plus 50 3 over 5 2 over 2 is equal to 50. To find when the temperature in the house will reach 40 degree Fahrenheit, we must solve the equation. 20 plus 50 3 over 5 2 raised to 2 is equal to 40. The solution of this equation, time 2 times ln of 2 over 5 over ln 3 over 5. And the time is equal to 3.6. Then, the temperature in the house will reach 40 degree Fahrenheit a little after 3:30 a.m. A cup with the water at 45 degrees Celsius in place in the cooler held at 5 Celsius. If after 2 minutes, the water temperature is 25 Celsius, when will the water temperature be 50 degrees Celsius? While solution, we know that T sub time is equal to T sub 0 minus T sub S times E raised to negative K T plus T sub S. And also, T sub 0 is equal to 45. And T sub S is equal to 5. And T sub 2 is equal to 25. Find T sub 1. And temperature of T sub 1 is equal to 15. First, we find K. T sub time is equal to 45 minus 5 times E raised to negative KT plus 5. Equal to 40 E negative KT plus 5. Then 20 is equal to T sub 2 is equal to 40 E raised to negative 2K is equal to ln 1/2 is equal to negative 2K. Then K is equal to 1/2 ln times 2. T sub time is equal to 40 E minus time ln times square root of 2 then plus 5 is equal to 10 equal 40E raised to negative t sub 1 times ln raised to 2 plus 5. And equal to t sub 1 equals to 4. Pasa mo ba?
Oh, yan.
Gwapo mo dito, Dok.
Oh,
Pero ganun picture.